Hello, in this video we will introduce kurtosis and show how to calculate kurtosis in R. So what is kurtosis? Kurtosis is a statistic which is measuring the peakiness or the flatness of a data distribution. So the data, if the data is, for example, coming from normal distribution, it is called bell-shaped. So it has very standard flatness, or the shape is not so peaky, not so flat. But if the data is not normal or from other non-normal distribution, so it may have kurtosis. It is not bell-shaped. So if we look at this figure, so in the middle, this curve is normally distributed, and it is called mesokurtic. But if the data has this shape, very flat shape, this is a probability density curve, right? If this density curve is very flat, so this is called platykurtic, and it is negative kurtosis for the data. And on the other side, if the data is very peaky, so the tail is very short, but the mode is very high for the density, so this is called leptokurtic, and it has positive kurtosis for the data distribution. And the kurtosis is the dimensionless version of the force moment about the mean. So if we look at this calculation, so first, if you want to calculate the kurtosis, you have to calculate the force moment. The force moment of the data means the data, each observation of the data minus its mean value, then take force in the power, then sigma together, then divided by n. So this is the mean of the force power of the difference between data and its mean. So this is called force moment, M4. And we calculate another item called S4. S4, which is the variance, the power. So this is also the standard error's force power. So S square is the variance of the data, and we take a power. So this is S4. Then the division of these two, M4 divided by S4, then minus 3, is called kurtosis. So how to calculate kurtosis? Then we will use R programming. So we go to RStudio. First, we load a data set. We set a working directory and read a CSV file and put the data into a data frame called data. So we show this data. So this data frame has only one column called values, this variable, and there are 30 rows. So 30 observations, and each item is numeric value. So we can calculate the kurtosis for these variables called values. Then we can attach to this data frame. So next we just can use the variables value. So first we show in a histogram of this data. As you can see, the data is not bell-shaped because there has some skewness on the right side, and its data also somewhat little flat. Then we create a function called kurtosis. So inside the function, actually, first you calculate the M4, which is the force moment of the data, and S4, which is the square of the variance of the data. Then division of these two and minus 3 is the return value for this function. So this is the kurtosis we will calculate. Then you can just use this function kurtosis for the values. Value is the data frames variable because we attached this data, so we can just use the variables in parsing for the parameter. So the point analysis of this point value for this kurtosis is about 1.29. But if you, because we use only one sample, right? This sample include 30 observations. But if you want to test again for another sample or run again, taking sample from the population again, you may not necessarily get the same result for this kurtosis. So this is why we have to use hypothesis testing. So hypothesis testing is just we set a null hypothesis first. So this null hypothesis, it means we assume first that the data coming from normal distribution and has no kurtosis, or the kurtosis is a mesokurtosis we have shown in the previous page. So we just assume this kurtosis is nothing, is no kurtosis, no positive, no negative. Then we test with this point value. So here, this is the point value for the kurtosis, and divided by the square root of the 24 divided by n. So this n is the length of the data. So square root of 24 divided by length, sample size. Then this part in the denominator. So kurtosis divided by this part. So this statistic will follow a t-distribution. So we just run. So this result is about 1.45. So because t-distribution, if you want to reject this null hypothesis, usually the critical value will be around 2 in the t-distribution. So this means this statistic only significantly larger than 2, then you can reject this null hypothesis that the data is no kurtosis. Because in our example, this calculated value is about 1.45. So this is substantially less than this critical value or rule of thumb 20. So we cannot, or say we have no significant confidence to say that the data has kurtosis in our sample. Or in other words, we will not reject, we will hold this null hypothesis that the data has no kurtosis. We look at this calculation again. So in kurtosis division of these 2 minus 3, then this value, if around 0, very close to 0, which means no kurtosis. If this value larger than 0, this is positive kurtosis. Positive kurtosis means this one has peaky value, peaky shape. But if the result of the calculation is negative, is significantly negative, so we can say this has platykurtosis or negative kurtosis because data is very flat and the mode is very low. So the highest frequency density is very low. So this is the negative kurtosis. So thanks for watching.